Hey, welcome everyone to this week's seminar. We're very happy to have Ferdia Sherry. So Ferdia is just finishing his PhD. I think he's currently technically a postdoc at the moment, but I think you'll be doing your viva in the next few months, something like that. So Ferdia is just been a student affiliated with the Untitled Chapter Institute for Access to Information and the Cambridge Image Analysis. And he was supervised by Cora Schonley and Matthias. Yeah, we're happy to have him today. Talking structure problems. Please, Ferdia, take it away.
Right. Thank you, Matt. Thanks to all the organizers for having me in this great seminar series. I've really enjoyed all of the talks so far. So yeah, I'm going to talk about some of the projects I've been working on over the past few years where we've sort of tried to have a principled approach to using machine learning for inverse problems. So we've had a few talks in this series already where inverse problems have come up, but I'll sort of set the scene here by saying in an inverse problem, we basically have these measurements y related to some ground truth image u star through a forward operator A and a noise model given by this fracture N. So generally we'll know the forward operator, or we'll have a good idea of the forward operator because we're looking at some kind of a physical process. So for example, a few weeks ago, Tatiana Buba, she spoke about the using machine learning, deep learning for problems in CT. So in computed tomography, we have the forward operator is the radon transform, which takes line integrals of the image as like the measurement model. So even if A is a linear operator, as for example, for this radon transform, the inversion process might be ill-posed in that there might not be an inverse at all, might not exist, but even if it does exist, or a generally you can come up with some idea of a pseudo inverse that overcomes at least this first point. The pseudo inverse is generally not going to be continuous, which is a big problem because you end up with noisy measurements, you end up blowing up the noise and coming up with useless reconstructions. So the field of inverse problems is quite, it's well established by this stage, and there's a very nice approach to sort of deal with this ill-posedness, and there's various regularization strategies, but one of the main ones is variational regularization, and that is sort of what we're going to take as our as a lifeline basically throughout this talk. So in variational regularization, the goal is to estimate our true image by minimizing a trade-off between a data fit and a regularization functional that sort of hopefully encodes useful prior information on the image. So this approach is nice for a number of reasons. Sort of two very nice properties are basically generically we have sort of a stability result in that if you fix this regularization parameter, your reconstruction is going to be continuous, and you have a notion of convergence. So might be slightly complicated to give it in full detail, but the idea is basically, yeah, if you have noisy measurements and you let your noise go down to 0, and then you can choose your regularization parameter in such a way that this estimated image actually converges to a pseudo inverse. So you could think of this as sort of statistical consistency. So variational regularization is it's a very neat approach, and people have come up with nice ways of designing this R. So the basic example would be Tikhonov regularization, which is just you take a squared 2 norm, but fancier examples have become standard as well, like the total variation of Rudin, Usher, and Fatemi, and sort of generalizations of this. But basically with this variational regularization approach, there's often you sort of reach a limit. All of these regularization functionals are sort of handcrafted, and also generally you end up with some tunable parameters that, sure, we have some kind of idea of how we should let these go to zero in the sort of asymptotic regime, but in practice you need to come up with some kind of heuristics for how to choose these parameters. So yeah, this really gives rise to the data-driven approach, I guess. You want to see, can we come up with a way to learn from data how to solve an inverse problem? And obviously, over the past few years, deep learning has really risen to has come to the forefront, and yeah, at least some people, a reasonably sizable portion, I think, of the deep learning community, sort of advocating for taking the direction shown in this famous bitter lesson from Richard Sutton, namely that all we need really is large models, large computation, and large amounts of data, and then any kind of mathematical cleverness is sort of obsolete, at least in the limit. So I think it's good to be at least a bit more. I think it's nice, at least from my perspective, to take the other side as well. So Max Welling came with a bit of a rebuttal. So some of these, a lot of these settings in which deep learning has really sort of broken previous states of the art rely on very simplistic settings, and also rely on us being in a problem where we can gather massive amounts of data. So we're not always in the setting, and we're not always in a setting where we can simulate our own data very well. So we'd like to argue that it still makes sense to come at this from with good models, and especially given that we have many years of inverse problems history behind us with nice models. It only makes sense really to use what we know about that to sort of inform our data-driven approaches. Okay, so this first project I'll talk about is a project that I did here with all these collaborators on learning sampling pattern for MRI using a bilevel learning approach. So yeah, like I said, there might be various free parameters of this variational regularization approach. So looking forward in MRI, we might have some kind of freedom of what measurements we actually want to take. And also, generally, we don't know what is the optimal regularization parameter. So, you know, if we have some kind of a gold standard to measure a reconstruction against, we are naturally led to sort of this bilevel optimization problem. We want to minimize the badness of our reconstruction and maybe somehow penalize certain parameters, while yes, this reconstruction has to satisfy the variational regularization problem. So yeah, and in what follows, this is sort of a supervised problem, but in principle you could come up with different you could do it in an unsupervised way. It's sort of an orthogonal issue to what I'm considering here. So generally this will be an empirical risk term, and here we'll have some kind of penalty, which we'll see in the future. So basically, yeah, so now the question is, we have this formulation, and how do we actually go about solving it? So the nice thing is we're going to assume that the lower level problem here is convex and smooth, and then the solution map is implicitly defined by this, and you can differentiate the solution map then using the implicit function theorem. And so in the end, we want to get some kind of a gradient of a loss, and then we end up with sort of this formula, which might look a bit complicated, but the main point to remember is, so yeah, we have to solve our lower level problem, and then we have to, and then the main point after that is we have to solve a linear system, a symmetric linear system. So you don't have to be necessarily too difficult about that. You can use conjugate gradient method or something like that. So yeah, that'll be basically the approach we take. So you could think about this problem a lot. Basically, the bilevel optimization problem in general is going to be non-convex, and in practice you see it's quite a hard problem, but basically if you follow these steps that I mentioned, you can apply whatever gradient-based first order optimization method, and you can use that to at least make an attempt to solve the bilevel optimization problem. So yeah, like I said, we're actually looking at the problem of trying to learn the sampling pattern for MRI. So in magnetic resonance imaging, or MRI, a combination of a strong magnet and smaller controllable magnets are used to essentially take samples of the Fourier transform of the ground truth image that you want to recover. And the point is, very roughly speaking, the more samples you acquire, the more time it takes to do so, to do the measurements. So you want to minimize the time that a patient has to spend in the machine. So it's natural to ask that we want as sparse a sampling pattern as possible while getting a good reconstruction. So the way we'll do this is we have our variational regularization problem, and we want to jointly learn some parameterization of the sampling pattern, which is, you can think of as just, I guess, a projection operator and the regularization parameter. So yeah, this slide is sort of illustrating why it's important to be careful about what sampling pattern you actually use. So obviously there's a whole wealth of compressed sensing literature that gives some kind of indication of how you should sample randomly, but on the left here we see if you sample uniformly at random, for example, in frequency space, you get a terrible reconstruction, whereas you can sample the same proportion in a clever way and you end up with a very nice reconstruction. So yeah, the bilevel problem we're going to look at then is of the form I mentioned before, where this penalty term encourages our sampling pattern to be sparse. So we can up the strength of that penalty term to encourage sparser patterns, and yeah, and hopefully if the optimization goes well, you end up with a combination of a sampling pattern and a regularization parameter that result in good reconstructions and a sparse sampling pattern. So yeah, I mentioned we're doing this through the sort of this implicit function theorem approach. So if you want to be careful about that, you want to maybe smooth the lower level problem a bit and add a little penalty for strong convexity. And this also has a nice effect on sort of the speed at which you can solve the lower level problem and the associated sort of linear equation you have to solve. So for just in terms of the details of what solvers I'm using for each of the parts. So I'm using this famous primal dual method from Chambol and Pock for the lower level problem, and then I'm solving the adjoint equation, so this linear system that we have to solve using the conjugate gradient method, and plugging this all into LBFGSB, because we have this, like I said, the sampling pattern is basically a projection operator. So this penalty is going to, so we'll parameterize it with values between 0 and 1, and the penalty will try to encourage both sparsity and that it's sort of binary valued. So yeah, and then you run this, and it takes a while to run, and you find basically, yeah, you get some very nice results out of it. And the nice thing is as well, so here we're sort of comparing two, I guess, standard regularizations that are used in compressed sensing. So like the variation that I mentioned before, which sort of encourages piecewise constant images to some extent, and wavelet sparsity penalty, which sort of well known from compressed sensing. And if you compare, so these are sort of kernel density estimates based on the learned sampling pattern, and you see that basically the pattern learned with the wavelet regularization has lighter tails than the TV one. So you actually get qualitatively different patterns for different regularizations. So yeah, one thing is, before here I mentioned this was sort of free patterns, but in practice you have some physical constraints that your machine has to satisfy. So one way in which this can be done is you can sample Cartesian lines basically. So we can parameterize our sampling pattern as a collection of Cartesian lines, and we can run the same procedure, and sort of reassuringly anyway, we end up with something that performs quite comparably to a greedy method that existed before for learning sampling patterns, but that doesn't scale up to sort of this free sampling pattern or to higher dimensions, and it compares favorably as well to sort of an uninformed variable density sampling pattern. And so the thing is also the benefit of, I guess, undersampling in MRI seems to become even stronger as you go to higher resolution images. So here I'm sort of showing you can sample just 5.7% with a learned pattern and recover the fine details of this phantom. So yeah, so the conclusion basically of this bilevel learning approach to learning sampling patterns is we can do it. It's nice that you still have that your reconstruction is a variational regularization reconstruction. So you have the stability of this approach, but in practice, it takes sort of a considerable amount of effort to solve these, because you have an inner optimization, this lower level problem that has to be solved to very high accuracy to get a decent gradient. And then you have this outer solver. So more and more people have moved towards a slightly different approach. So this unrolled iterative scheme approach that I'll describe in the next bit as well, that sort of allows you to cut down on your computation time by a good bit, and also allows for more flexibility in the learned reconstruction. So sort of the next project then I want to talk about in this direction is this paper that we published in Inverse Problems, where basically, yeah, we're trying to figure out how can you incorporate this group equivariance, which has sort of become a hot topic over the past few years in deep learning, into a learned reconstruction method for inverse problems. And specifically, the learned reconstruction method is going to take this form of a learned iterative scheme. So although it's sort of a hot topic and it was talked about a few weeks ago in this seminar series as well, I'll give a bit of a background on like why should we care about equivariance. And so this is a bit of a contrived toy example maybe, but basically here I've trained an ordinary CNN, so purely translationally equivariant CNN, and a roto-translationally equivariant CNN to denoise this image consisting of horizontal stripes. Then when you turn this image and you try to test it on an image with vertical stripes, the ordinary CNN fails miserably because it hasn't seen anything like that during training, and it doesn't know how to cope with this rotation. Whereas the equivariant one does exactly just as well as it did on the training example. So the point is, we want to have, often we'll be in a setting where we want to have some kind of robustness to some symmetry, basically. So generally, it's probably, maybe not universally, but it's often makes sense to ask that a denoiser is going to be going to have more than just translational symmetry. So yeah, in terms of formal symbols, we'll so I think this was mentioned then as well in the talk a few weeks ago, but we'll assume there's some kind of group actions on two function spaces, and we'll say, or on two spaces, I guess, that this operator maps between. And we'll say that this operator is equivariant if it plays nicely, basically, with the group action. So yeah, the standard example being convolutions play nicely with translations. So in this specific case, we're going to be looking at the case where we have images, and potentially these images take vector values, basically, and these vectors are going to be geometric objects. So this nice image from this paper I mentioned here is really illustrates what I mean. So we don't, if we apply a symmetry operation, we don't just want to make this change in the domain. We really have to apply the relevant part of the symmetry operation to sort of the vectors as well. And so the way that this is formalized is, you're going to assume that, so we have this here we're going to be only looking at roto translations and maybe reflections. So our group takes the form of this semi-direct product, and we sort of have a choice of various options for this H. So basically what this, so formally what this means, what I was saying, that the vectors have to transform accordingly, is we'll have some representations on these, on basically the range spaces of these functions that say, this is how the vectors should transform under the action of the group. And then you end up with sort of the overall induced representation on the function spaces taking this form. So exactly what I said, you move the vectors and you have to transform them as well by this part. So I guess one question you might ask is, we're doing neural networks, so neural networks are generally thought of as, okay, we're alternating a linearity and a non-linearity. So can we come up with equivariant linearities and non-linearities? And basically there's this nice result that says, at least in this setting that we're in right now, if you want to have an equivariant linear operator given by an integral operator, then it has to be a convolution, and this convolution has to satisfy sort of this extra constraint. And so this constraint might, at first sight, might not be clear to how you would solve it, but basically the answer is you can solve it ahead of time. So once you specify pi x and pi y, you can solve it ahead of time, and you basically end up with your convolution kernel has to be a a circular harmonic times a radial part. That's how you get this equivariance. So the a nice side effect of this is basically we can get these equivariant convolutions just by building on existing convolutions and restricting the kernels that we use. So basically not any, but if you have an equivariant convolution, you could implement it as an ordinary convolution as well. So nonlinearities are potentially a bit more difficult than they are for ordinary neural networks, but you can still come up with various ways of making equivariant nonlinearities, including sort of like this self-interaction, or you can have various parts interacting with each other. And if you put some constraints on your representation, you can also basically use any normal activation function, just a scalar activation function, and you'd be okay. And yeah, I've sort of left the bias behind, but you can include this bias inside your nonlinearity if you want. So now the question is, there's this existing machinery of equivariant neural networks, and we're trying to solve inverse problems. And we sort of come at it from the variational regularization approach. But in general, the variational regularization approach is not going to, I guess there's the question, what does it mean for it to be equivariant? Because the forward operator generally maps a space that might be symmetric. So like this nice image space to a space that might not have symmetries. So if your measurement space might not have a nice shape and it might not have nice symmetries, but you might try to ask what happens if you apply your forward operator and then your reconstruction. And it turns out even that you can't really expect to be equivariant, because basically you can make information disappear through your forward operator, as sort of illustrated here for an in-painting problem. So if you rotate your image first and then cut out this bit and then try to do a TV reconstruction, you get this. Whereas if you revert or you do it in a different order, you get this image, which is actually different to this. So we can't maybe generally expect this overall pipeline to be equivariant, but some parts of it might be still. So generally, if we're solving this variational problem, we're going to use a splitting optimization method. And often it's going to take, like the basic form is the proximal gradient method, or the forward-backward splitting method, sort of illustrated here, where you split it into, you're taking a gradient step along the data fit term, and you're taking a proximal step, which you can think of as just a denoising step. So yeah, so even though the overall pipeline is not equivariant, you can generally you can assume that your regularization function has some kind of invariance, and this then results in the overall proximal operator having an equivariance property. So this then is going to be how we incorporate equivariance into a learned reconstruction method. So as I sort of alluded to before, probably the state of the art at the moment in learned reconstruction methods is this unrolled iterative scheme method, where you take an optimization method like the proximal gradient method, and you truncate it to a finite number of steps, a small finite number of steps, and you replace some parts of it by learnable parts. So the point is going to be, we have a decent idea that we can model this prox, which is not necessarily a proximal operator, but you're hoping that it somehow emulates a proximal operator by an equivariant small neural network. And that's sort of then going to be the comparison you do. So you can compare, the standard approach would be you just use translationally equivariant neural networks, so CNNs for this. And what do you gain anything when you go to roto translationally equivariant neural networks? So yeah, this is just sort of a schematic approach of how the various inputs lead to the outputs. And I sort of glossed over the fact that you can allow for a little memory state here as well. But yeah, I mean, these memory states are sort of motivated in general anyway by the fact that they also exist in accelerated normal iterative schemes. Okay, so yeah, one thing I didn't really mention before yet was, so I said you can get these equivariant convolutions by basically taking a convolution with a circular harmonic, but in practice you're going to have to sample this circular harmonic on a small grid. And generally in neural networks, even for these equivariant neural networks, people take sort of 3x3 filters, so you have to sample your circular harmonic on this. So you run into some problems maybe with aliasing. So it's not clear. In principle, theoretically you can use you can have equivariance to the whole rotation group, but in practice then it turns out you generally end up doing better if you sort of stick, for example, just to on-grid rotations. So I guess that's what we do in the future, in what follows. So one of the things people think about, or one of the things people say as a positive of equivariant neural networks is they should have lower sample complexity. It takes less information to fully specify an equivariant operator than it does an operator that doesn't have symmetries. So you're hoping then that this sort of comes back and you see it in terms of better performance with smaller training sets. So you can sort of see this effect here. And another interesting thing is, so even though the overall pipeline is not equivariant, you can test so you can test on rotated images, and you find that if you use these equivariant models for the proximal operator, you have more robustness to these to the rotated images as well, so sort of unseen rotations. And this is just sort of a comparison of some reconstructions then for a low dose parallel beam CT problem. And you see a similar sort of thing, MRI problem, where you get a bit of a gain for smaller training sets, and you actually see that the equivariant one does a bit worse than the ordinary one once you get to large training sets, because you should keep in mind this comparison that I'm doing is basically the ordinary one has enough capacity to completely emulate the equivariant one, so it's more flexible. So if you feed it enough data, it's probably going to do better than the equivariant one, at least for these images that are like the ones you've seen in training. But then you still get this robustness to unseen rotations. So yeah, so this so in this approach we've sort of said, okay, you have a method that is inspired by a splitting method, and this means we have to model a proximal operator as a neural network. And one of the things you end up with if you do this in this framework, or for example, in a plug and play framework, if you want to have provable convergence, is you want to come up with some kind of constraint on how stable this learned proximal operator is. So basically a proximal operator of a convex function is always going to be non-expansive and a bit more, but you also need this kind of a property to actually then use these operators in a provably convergent iterative scheme. So that sort of brings me to this last project I want to talk a bit about, where it's basically, it's based on a chapter in this survey paper that we wrote, and it's focused on designing Lipschitz neural networks, basically. So Lipschitz neural networks have, of course, been quite a hot topic over the past few years because, for a few reasons. So I give these examples, but there's definitely going to be more as well. But notably, the people saw you can train a neural network to achieve state-of-the-art performance on a classification task, but that neural network is still going to be susceptible to adversarial examples, which is sort of a major problem if you're concerned about actually using these things in practice. So sort of to overcome this, people have already been thinking about enforcing Lipschitz constraints on the classifiers, that kind of thing. Another thing is what I mentioned here, that basically if you want your learned component to be a part of a bigger thing, potentially an infinite iterative method, you want to be able to guarantee that it has certain Lipschitz properties. And then of course there's this application as well to generative adversarial networks, where they sort of need them as the critic for this Wasserstein distance. So so to some extent, this project I'm talking about is maybe a bit of a toy project and looking for an application, really, because to some extent this Lipschitz neural networks thing is solved, right? Because the Lipschitz property plays nicely with the compositional nature of neural networks, and linear operators are going to be Lipschitz with sort of a controllable Lipschitz constant. So if you end up with your ordinary feed-forward neural network, no skip connections, you can control this Lipschitz constant. And there are well-established ways now of actually enforcing certain Lipschitz constants by basically spectral normalization. So this is all nice and well, but people also like the ResNet model, right? So the ResNet model says we want to, instead of having this plain feed-forward network with no skip connections, we want to allow for some skip connections. So basically each layer of our neural network here, depending on how you want to call it, a layer, is going to be itself a small perturbation of the identity. And so if you try to apply this spectral normalization approach to make a Lipschitz ResNet, it sort of doesn't work, in that you end up with, if you use spectral normalization on each of these smaller networks, you're going to end up with this being only guaranteeably 1 plus epsilon Lipschitz, and your Lipschitz constant growing exponentially with the depth of the network. So basically what we'll do then is we'll say you can come up with ResNet styled architectures that are provably one Lipschitz and basically motivated by ODEs in a similar way to this famous paper by Haber and Rotolo. So sort of the basic idea is we have this this ODE flow, and it's well known, and you can see quite easily just by a Taylor expansion that this flow map is only going to be non-expansive, or it's going to be non-expansive if and only if we have sort of this this monotonicity condition. And so if sort of looking forward to what we're going to be doing, you can think of this already as this vector field. If it's just going to be a gradient of a potential, then, or negative gradient of a potential, so this is a gradient flow, then this is equivalent to asking that the potential is convex. So if we have this, we can compose these flow maps, and we end up with a non-expansive operator. So, and then sort of a simple observation is just, you can always get sort of a learnable convex potential, or there's always going to be an underlying learnable convex potential if you parameterize your vector field in this simple neural network way. So yeah, that's nice, but in practice we don't have access to this flow map, and we have to do some kind of numerical integration, and this this non-expansiveness, okay, it's not non-expansiveness under this condition is not preserved universally by numerical integrators. So some implicit methods, like the implicit Euler integrator, have this stability property, and you end up basically then you're composing proximal operators as your neural network, and people have done this, but for this to be computationally feasible, you have to sort of severely constrain your weights. So for example, you have to constrain them to be orthogonal or something like that. And one major concern then is, it's well known in the ODE theory that an explicit integrator is never going to be sort of unconditionally stable. Then the numerical integration is also non-expansive. Luckily, in practice, there's a sort of a partial alternative, and that's, you can replace the condition on the vector field by this monotonicity condition, or sometimes it's called a one-sided Lipschitz condition. And if you have a Runge-Kutta method, you can, given the parameters, you can compute a radius r for which it satisfies the so-called R-circle contractivity condition. And then once you do this, you get a constraint on your step size that ensures that your numerical integration will be non-expansive as long as your step size is small enough. And so this condition, if we're thinking again about the if we're thinking about this convex potential in the background, this condition then just translates to the condition that that potential is smooth, in the sense that it has Lipschitz gradients. So we can continue to use this model, and we just have to do spectral normalization. So our non-expansive ResNet is going to be composed of sort of this sequence of numerical integration steps along these potentials, where we're making sure that we have this constraint, and we can ensure this constraint during training just through this spectral normalization. So for the Euler method, it takes a particularly simple form, but sort of a potentially neat thing anyway is there are higher order integrators you can use, although I'm still trying to figure out whether there's ever any point in doing that, because at least in the applications I've looked at, there wasn't. So you can say a bit more about it if you use the explicit Euler method. So I mentioned that a proximal operator is Lipschitz or non-expansive and a little bit more. So this little bit more is that it is also actually one half averaged. So it takes this form with alpha equals a half. And this is a particularly nice thing because if you have an averaged operator as opposed to just a non-expansive operator, then its fixed point iterates are going to be convergent, which is nice if you want to use this in practice. Whereas if you only guarantee non-expansiveness, you don't have this. So it turns out in this same setting, you can further constrain your step size or the norm of your weights to ensure that any layer of this proposed architecture is averaged. And then if you compose these things together, you end up, the composition of an averaged operator is averaged. So you end up with something that has convergent fixed point iterations. And so again, I guess a toy example here, we're just trying to learn 2 ResNets on 6 points to learn the absolute value function. I guess you could say probably neither of them does a particularly great job, but at least we know if we're guaranteeing the side of our training set, our learned non-expansive network doesn't do anything strange, whereas the learned ResNet may violate this non-expansiveness. So yeah, I guess I was sort of alluding to the fact that we'd like to use these as models for proximal operators, basically, right? So as models for denoisers. So in that case, yeah, you want to train your network, your non-expansive network or your average network to solve a denoising task. And here I sort of set side by side various approaches. So where we allow some scaling, so we scale up output so that in fact the network is not non-expansive anymore, but it is gamma Lipschitz, or we use this residual learning approach. And here we're comparing to sort of the DN-CNN, which is sort of a benchmark for denoising, and also uses this the residual learning approach. So I guess the somewhat disappointing thing is if you have this unskilled network, you don't do that well, and you have to go up. Once you get to this gamma equals 1.99, which is sort of a magic number, because this is a point at which you can still use it in some sense. You can use this now to plug into the results of a paper I mentioned here, this paper. Then you sort of get to sort of a decent performance, but I think it'd still be interesting to see, like, is this so it seems, yeah, if you're really looking for something non-expansive, the it might impose too many constraints on your denoiser. Is there a better way of training these denoisers? So this is just then a side-by-side comparison of the various methods. So like trained in a non-residual way here on the top, and then in a residual way. And once you allow this gamma to be as large as you want, then basically you reach the level of the completely unconstrained network. So somewhere, probably in practice, then you want to find somewhere in between where it gives you some kind of a guarantee while also given decent performance. So yeah, I've sort of tried to convince you in this talk that it pays to be principled about how you use machine learning to solve inverse problems. There's at least one problem that I think is still very interesting, and I think it's sort of within reach, and that's, I mentioned this fact that the classifiers, state-of-the-art classifiers, tend to be susceptible to adversarial examples, but it turns out that state-of-the-art learned iterative methods, like I showed before, are also susceptible to adversarial examples. So can we sort of be more principled about this still and come up with sort of a similar theory as exists for variational regularization? So basically this stability and maybe convergence. So this result that is akin to statistical consistency. And I'd be very interested in sort of pursuing that further. So yeah, I'm happy to answer any questions and hope you enjoy.
Okay, thank you very much, Ferdia. Yeah, if you have any questions, please put them in the chat or feel free to unmute yourself. Yeah, I mean, maybe I can start off. So I think at the start of the talk, you kind of said, how you kind of wanted theoretical results to things like consistency and stability. So, I mean, are you able to show something like consistency for any of these networks?
So for most of the things I was doing there, you don't have that. So for the bilevel